All right. You're good to go.
Alrighty, thank you, Dr. Nimi. Well, hello, professors, TAs, and members of the board. This is Group 9's final oral presentation for the turbidostat. The inventors in our group are Dylan Atterbury, Alexa, Peter, Bert, Ryan, Andrew, and myself, Joseph Pruger, working with partners Northrop Grumman, Cummins, and the UF Biofoundry. Here's an initial rendering of our final design. I'll go over each specific component later on in the presentation. So our Hedgehog concept mainly focuses on three things: creating more open source data through the experimentation and more efficient benchtop footprint that we have in our design, our increased design flexibility, including modular design with reattachable fixtures to enable future iterations of the design, or if you need to add anything new to it, you can. And using OTS parts in conjunction with custom-made parts will help enable cost reduction in our design. The overall benchtop footprint of our microbioreactor is 1.2 meters in length by 0.739 meters. And that distance specifically is from the outside edge of this button to the back of the vent on the back of our device, not this length. The length across of the bioreactor is also equivalent to the height of 0.6 meters, which meets the customer try to have requirements. Here is a rendering showing a table that the microbioreactor can sit on. The table is 5 feet long as just a little scale to judge the bioreactor on. I'll give it a few seconds to take it in. Okay, moving on. Going over some customer requirements based on how our design met those requirements. Our turbidostat can accomplish the fluid dispensing and disposable needs by having a XYZ gantry style track system, which I will go on further in the middle of the presentation. 2 nozzles, which include fluid addition and subtraction. One of these nozzles is separated for waste disposal and sterilization. Our fluid dispensing and disposal system is generated via peristaltic pumps, which include accuracy and precision. And this is all in control with our controller system. For our gas dispensing and disposal system, we utilize pinch valves and an additional sensor to regulate how much gas and on or off in the system. We have the ability to provide all 5 requested gases to the device. And we incorporate a vacuum and compressor for safe gas disposal into a waste container. Our optical system has a light sensor, which is also attached to the gantry system for the ability of XYZ movement to capture OD readings of each well plate. We have necessary light strips inside our tube containers, which I'll show later on in the presentation as well. And this system is also in control with the controller system. Our controller is a UI interface that is attached to the housing unit and allows for system programmability. We have a manual shutoff button, which is not just press. You have to pull out and then twist to push in the button, which allows for not easily being able to knock into the button and turning off the device. And we also have an autonomous safety limit shutoff. We have an adequate warning visibility based on the light that was on the front of the control system, and it controls and communicates with the rest of the system. Our temperature control unit consists of heating strips that are on the outside exterior containers of the compartments that we've made for the conical tubes and culture trays. We utilize an ambient cooler to cool the system if temperatures reach 70 degrees, which is the maximum based on the customer needs. And this also communicates with our controller system. And we can manipulate temperatures to have different experiments going on at the same time. Our shaking and tray system incorporates separate housing chambers. And in our system now we have 2 devices, so we can have 2 separate experiments going on at the same time. And it works in conjunction with the housing chamber as it sits on the floor. And our shaking mechanism allows for all 3 required movement patterns, which are linear, double orbital, and orbital. And we have an animation after our presentation, which we'll show of the movement patterns. And then our housing unit is just a conglomeration of each of the other subsystems, as it includes and houses all of the other subsystems. It also includes a sealed door, so no interior gases can flow into the lab room and exposing anyone. And now to go over the technology readiness levels, Drew or anyone else could help me explain this part of why we chose level 2.
Yeah, so based on the NASA defined levels for the TRLs, actual laboratory testing had to be done to reach a level 3, although in some of our systems, we believe our analysis would suffice for that. So we went with the safer technology readiness level of level 2 for the majority of our systems.
And the total TRL would achieve a level 2 because that is the weakest link in the subsystem, so it cannot exceed any of the other subsystems. Our key design features that our group has noted was our fluid handling subsystem and our shaking and trays subsystems. Our fluid handler, as I previously described, has 2 nozzles, an XYZ gantry for assisted motion, an enhanced Z directional movement with a rack and pinion device to allow the device to go even further down into the system. And we also have autonomous fluid addition and subtraction with a hook to open the container to allow for this autonomous motion. And our shaken and tray system has uniform heating sleeves and optical density LEDs included within the capsule. Here are 2 CAD views of our fluid handler, a close-up image here showing 2 tubes along with bevel gears and a motor. And here's our gantry subsystem. Alexa can explain this later on when we go over the CAD portion of our presentation. We also have position control motors on the ends of the gantry to help with the movement along the sliders. Here's a CAD view of our shaker. We also have animations available after the PowerPoint presentation. Here's the housing and then the shaker tray holder in which the culture plates or the culture tube containers will rest on. Here's the views of our trays subsystem. This is the container that was created to house the tubes with our heating strips. This is the container lid with the hook, or the latch rather, and then our LEDs are underneath the well plate. So the overall cost of the system was a conglomeration of OTS parts, off-the-shelf, raw material, manufacturing, assembly, and energy costs. The off-the-shelf costs contribute most of the cost to our system. And we are currently also revising our assembly cost as new additions was made. And so why do we want to prototype the turbidostat? Well, through the modular design of 80/20, we have movable and accessible features that have the ability to be changed out based on the way that they're screwed onto the device and in different patterns. Our total cost is underneath the required $10,000 limit, which means there's a lot of fluidity to add things to the design if needed later on. But this is a final design, so we think that it's optimal. We have autonomous fluid addition and subtraction without the need for a robotic arm to either move the culture plates or do any other assembly that we need. And so there's a lot more room available inside our design as well. And also, who wouldn't want to prototype this based on the quality of this render? Here's a wrap-up slide, just showing the initial render that was on the first slide of the presentation. And I think before we do any questions, we're actually going to turn it over to showing our animations and running through our CAD models through Alexa or Bert.
Yeah, I'll start with an animation for the just an overall 360 view. Can you guys see my screen?
Yes.
All right, great. This is just to give you an idea of better scale. And then I have one more of the gantry doing its thing, which just demonstrates the overall ability of the fluid handling system to reach any area within its range. With that, I'm going to hop over to the CAD model. Did we want to show the other animations for the shaker now, or ask for questions first?
We can show it now.
All right.
I have that pulled up, unless you want to show it, Alexa.
No, you go ahead.
Okay.
I'll stop sharing.
Here's a linear shaking pattern. Haven't actually created an animation for the double orbital pattern, but it's a little bit. Yeah. Issue with the tray.
The tray.
Yeah, the tray's not there, but that's
I
okay.
think you're-
That's just simulating the orbital motion.
So is it 2 stacked motors?
Yes. Yes. We can go into further explanation of that if you needed. Bert, could you go over that configuration?
Yeah, so we have 2 stack motors. Our initial idea was to constrain the rotation with extension springs, but I'm actually moving on and working with rails now to prevent any rotational motion. But essentially, to get the linear motion, we'll just go, invert the direction. But each motor will be spinning in opposite directions and 90 degrees out of phase. To get the orbital, we could have one motor on, and then for the double orbital, we could have the motors moving at different RPMs. The top one, twice the RPM as the bottom one, and every half rotation of the bottom motor, the polarity on the top motor would invert.
Yeah, based on the controller settings. And then let's hop into our main CAD file, Alexa.
Right. So, okay.
It might be a little laggy because we got a lot of things going on.
Yes. Hopefully SolidWorks will hold out for us. So I guess we can start with fluid handling because it's the main thing. We have our fluid handler here, mounted on the gantry, as we said, and it can actuate around to the plates that are on the shakers. These plates are boxes there. Hold any standard size well plates from 6 all the way up to 384. And then these boxes are made to hold the conical tubes, 15 milliliter and 50 milliliter, interchangeably. We've got our controller interface, emergency light indicator, and emergency stop button. Peristaltic pumps for the fluid dispensing system are mounted to the back wall. And then around the back, we have the ports for the different gases to be brought into the system and also to be disposed of. This is just an example of the fluid gases being collected in a chamber. We also have our ambient cooler. We added a cover to it as per request from Design Review 2. And going back around the front, we have our door, which is currently open, but it closes and it has a compression handle so that it can be fully sealed down onto these
Ceiling
sealed here
frames.
in the frame.
Yeah. And then we also have a sterilization cup inside that the fluid handler can also, you know, handle the sterilization as to not provide contamination into any different well plate or conical tube. So basically that's our whole design in a nutshell. Any questions?
All right. Good job, guys. That was the fastest 30-minute presentation that we've had yet. We'll open up the floor for questions if anybody has them. I will hold my peace until others have had a chance.
Hi, I'm Chris Reich, assistant professor in microbiology. Could you walk me through the liquid sterilization process? So the liquid handler is just using tubes of some sort, and then that would have to get sterilized.
Yes. I'm actually going to open the fluid dispensing subassembly if I can manage to select it properly. Let's see, I'm gonna go with this one. Just so I can zoom in on it better because the entire assembly is a little bit large. All right, so this is our fluid handling system. Basically, we would like to have one tube for inputting fluids and one tube for
Subtracting fluids.
moving fluids, yes. So that you have different nozzles and we won't be having cross-contamination
Yep.
between disposing of waste and adding new feed for the bacteria and such. So I guess we could say this would be disposal, for example, and we have the container full of disinfectant solution where the disposal nozzle can actuate over there, dip down into the disinfectant, which is 70% ethanol solution, I believe.
Yep.
And also, you know, sucks them up to just clean out the pipes as well, or the tubes.
And I might add that you can do this with both nozzles because the pumps can work in either direction.
Yes, that's correct. The peristaltic pumps are capable of going in reverse, so either of these nozzles could do
Then
that.
the sterilization fluid would be some ethanol solution.
Yeah, the 70% ethanol.
And the volume of the tubes would be dictated by their diameter. Do you guys have an idea of what that would be?
3/8 of an inch diameter or 9 millimeter OD for the tubes.
What would your max and min volumes be with that?
Drew, do we have calculations for that?
Volumetric flow rates?
Well, yeah. I mean, what's the maximum you could take from one chamber and put into another without going back and forth, I guess?
Okay.
No, we'll have to make those calculations.
So move from one well to the other.
Yeah, or if you're, yeah.
Okay.
Or if you've got a 15 mil centrifuge tube, how much of the volume of that can you pull out to dispense amongst a bunch of different ones potentially? I see somebody scrambling away in a notebook right now.
Yeah, I'm writing these notes down so we can add to our final design report. Yep.
How do you guys plan on manufacturing that assembly?
The fluid handling assembly,
Yeah.
this section,
Yeah, the whole outer frame of it, as well as how do you plan on assembling the motor in there?
well, the outer frame is a piece of tubing, either aluminum or possibly a chemical resistant plastic.
Is it a nominal size tubing?
Yes, it is.
Okay.
I believe it's I can just measure it. I can't remember off the top of my head.
Yeah, Ryan, that was assembling that was a great question.
Is the motor just set in there, or is the motor like actually mounted to something inside that tube?
All right, so that is a nominal 1-inch tubing. The motor is probably going to be mounted with a bracket. It is not shown right now, so I do not have enough time for that. But
yeah, because my big concern would be trying to get the motor in the right location. And typically your motor has a flange on the front of it that you're mounting with. So you're going to have to either mount the motor onto the flange and then stick it all the way down inside and somehow get that perfectly aligned. So it might be easier to design it so that you have kind of a class, like a shell system, so you can get inside of there versus trying to fidget and get the screws through the tube.
that's definitely a good idea.
So you're recommending sort of like the tube is in like 2 pieces, so you can open it up, see the inside, and then like clamp it down?
Well, yeah, it would make it a lot easier for us in terms of assembling if you could actually get to the inside of it versus trying to have to just
shell.
Make it a flat back piece with whatever mounting flanges you need, and then just have a slide-on plastic cover to cover it up. Like, it's how you route wires through a monitor stand. Like, I can reach behind my computer right now and pull off a plastic sleeve.
Yep.
So, Chris, did you have any more questions about this thing as one of our customers?
What about, so inside of the chamber, obviously you can fit different size plates or tubes. What about the atmosphere in terms of the amount of moisture in the air? Is there a way to control that, or?
We've included like temperature sensors. There's actually a sensor inside the fluid handler. Alexa, if you could zoom in. We have temperature sensors there. I don't believe we have humidity sensors. But we sure can add it. And also for gaseous environment, the tubes will actually be connected individually to like the containers of the culture plate containers and the tube containers too. So no gases will be actually inside the interior other than in those compartments.
Okay. So then it would be easy to, you wouldn't have to control the humidity in the entire chamber, just in that.
No.
That should be easy. So yeah, evaporation of small volumes of liquid is a.
Right.
Yeah, all these are sealed and stay sealed unless fluid is being added or subtracted.
So how are they sealed?
The lids are just shut. Like I guess what I was saying is the microplates are shut inside a much smaller.
Yeah. And then the same gantry that has the liquid handler would open and close those?
Yes, it has that hook. Yeah.
I actually have an exploded view. I can show this a little bit better. So this is an example with a 384 well plate put inside of the box. And these are all the LEDs for optical readings. It's the lid and the heat strips. So not sure if that's helpful, but
yeah, that's helpful.
Here.
The optical readings, is there any science behind that in terms of how you would record those measurements and convert them to a valuable or useful number?
Well, to record the measurements, we have a photodiode attached also to the fluid handler.
Yeah, it's over here. I'm not sure if the full assembly let me show it. Yeah, it's over here.
Oh,
It's here.
So that photodiode would be what records.
the optical
Optical
density
density.
readings.
Okay.
The plan was to have a photodiode that could be calibrated. You know, you get a voltage output, and then that could, because we weren't entirely sure how the researchers wanted to, you know, calibrate their optical reader based on like what kind of experiments they're doing, and you know how the bacteria grow, and what nutrient solutions are going to be in the wells. So it made sense to us that it would have to be calibrated for each specific situation.
Yeah, especially also with changing the volumes of the different plates and tubes and such. You're gonna have different path lengths and such. So yeah, that makes sense.
So I've got a question for you guys here. Where's the insulation to keep the external, the outside of this from getting too hot? I didn't see any discussion about the heat transfer and keeping the outside of this thing from getting to be a nice toasty 70 degrees as well.
Yeah, so we
So
actually,
we-
oh, you got it, Drew? Okay.
Yeah. So we actually did the heat transfer analysis in the preliminary design report, and we set it up. I'm scrolling through it right now. We set it up as a thermal circuit to determine the surface temperature, and we chose our high density polyethylene thickness based on that, and we determined that we needed.
It should be around like 5 millimeters in thickness to accommodate for a change that would not allow the outside of the device to exceed 50 degrees Celsius, which is as per the customer needs.
Yep.
Okay.
We'll also include that analysis in our final design report as well, because we think that's a pretty solid analysis that should be included.
And then you had this, like you said, you had like this LED array or something like that down at the bottom of the plates.
Right.
So is that LED array for a specific size well plate?
So what we were
That
figuring
was actually
is,
an analysis.
yeah. What we were figuring is
Yeah,
that,
go ahead.
yeah, based on like the size of the well plate, the controller would contact with optical, LEDs to turn on a certain amount of LEDs per experiment based on the size of the well plate to be able to actually record the optical density.
Right, but okay. So I've got a 384 well plate.
Mm-hmm.
I can go and put, I'm just talking, if you can visualize this, I can have an LED underneath each one of those 384 wells, so I can do all of those individually. Right? It's like a single individual LED. That's your LED array. But now if I've got a 6 well plate, I'm going to have dark spots in that well where it's not going to be properly illuminated because I'm not actually diffusing my light effectively, or I don't have a perfect circle. Things aren't going to line up correctly. So especially with everything being in that close of proximity, that's my major concern here with having that. I also don't know exactly how a microplate reader works, so it might be perfectly fine because I've never dug deep into the bowels of one of those. But just that's my concern here is that if you go to a different plate configuration, you're going to have weird optical artifacts due to light being funny.
Right. Drew, were you going to have a different answer to that?
No, I was just going to say we were planning on calculating the amount of LEDs that we'd have to turn on for the different size plates. like based on the area of the of like the
well.
circle in the well plate, and then the area of each LED to optimize as best as we could.
Was going to suggest that it might be possible to take readings from, I mean, when the optical readings are going to be taken, the fluorescent lights that are included in the chamber, those are going to be off. It's going to be completely dark and closed off from any ambient lighting in the laboratory. So I was going to suggest that it take maybe multiple optical readings from one well plate using individual LEDs, or what Andrew just suggested, multiple LEDs come on per well plate. But that might be tricky.
Yep.
Yeah.
Okay. Do we have more questions?
I don't know if anyone has this question, but we did provide calculations for ambient cooling in the system. To cool from the highest degrees in the system of 70 degrees to 4 degrees, it'll take around 8 minutes. And to cool from ambient to around 40 degrees Celsius, it would take around 2 minutes.
That's fast. That's really fast.
From 20 degrees to 4 degrees.
Just like all of your times are faster than I would have thought. So
I have a quick question about your XY motion. The first question I have is, are you guys threading the aluminum blocks? And if you are threading them, do you see any potential for the fact that they might wear out over time as you run the lead screws through them?
Alexa?
Yes, we are threading the blocks, and we have not done an analysis about the wearing the lead screws out at this time.
Okay. So, and then my other quick question is, are you guys confident that the 80/20 is going to be, I guess, straight enough? And then the mechanism that you guys are essentially using a clamping system, right, to constrain the motion linearly. Do you guys have a way to like adjust the force on the like the force of compression on the 80/20? Or is it like kind of you just bolt it on and it is what it is because the holes are drilled in one location?
Yeah, I think the latter.
And then our reasoning for 80/20, we took from the try to have requirements for modular design to allow for future modules to be added on. Because with the T-slot already in it, we figured that it would be easiest to mount future additions to the product that way.
I've got a whole host of ways to debunk that entire statement. So, I mean, particularly for the frame, making the frame out of 80/20, you're not going to be disassembling your external frame if you're adding a module to it. So it makes no sense there. I agree. The T-slot does make it great to add extra stuff onto it, but so does a bunch of 1/4-20 tapped holes on 1-inch centers, which is how every optical laboratory table, well, actually they're M6 holes on 25mm centers. That's how they're all set up. It's a flat table with a bolt pattern on it. Another great way to get modularity. So it depends on, so as an engineering designer designing a product, you kind of get to make the call on how you want your system to be modular. So you can use somebody else's system, but now you're stuck using 80/20 and their T-slots and all this other stuff. Or you can go and be like, all of our stuff is going to have a 100mm square fixturing, and all of our modules just need that, and they'll drop it and bolt in. Great, done. You know, M6 fasteners with 100mm square. You know, it's the same thing actually as a VESA 100 TV mount. Well, great. Now you can like essentially use VESA TV mount adapters everywhere. There's other options for modularity, not just 80/20, which you guys are all comfortable with from DML. And I rag on 80/20 I was a DML TA for 6 years. So I'm not ragging on it because it's not useful. I'm ragging on it because it's not useful here.
I think it was more the familiarity to it. As Dr. Traum was saying before, how he joined, or he was teaching a rocket team, and then he told them to use the composite material instead, and he got better results. So I think it's kind of the same thing in this system. We just went with it because familiarity, and you know, the results work. We have cost budget to allow for it too.
Well, I'm willing to bet that aluminum angle, 90-degree aluminum angle, would have been less than half the price.
No, yeah, I agree.
So, but, do we have anything else? If not, I am going to send out the link then for the landing page with the presentations. So anybody that's going to be coming to the next presentations, the meeting link or the landing page for the agenda is there. Thank you guys very much for your